Welcome to Asteroid Day. My name is Jim Zimbelman. I'm one of the scientists working here at the National Air and Space Museum. And as part of a global audience today, we're glad to be partnering with Asteroid Day events around the world. Because of that, if you have questions, I would encourage you to go to the NASA Facebook Live page to submit questions, either during the presentations or during the question time. And to moderate today's activities, I would like to invite Cheryl Reed to the platform. She is working at the Applied Physics Laboratory at the Johns Hopkins University.
Thanks, Jim. Well, again, welcome to Asteroid Day. We're here in the nation's capital at the National Air and Space Museum in this beautiful Moving Beyond Earth gallery. And Asteroid Day goes back to about 2015. It's an international event. It was put together by folks who saw the need to bring the planetary defense awareness to the forefront. It was a UN-sanctioned event. We're quite fortunate today to have a great cast of speakers. What our format will be, we'll have the speakers give their talks. You'll have a chance after each speaker to do Q&A. Those of you in the audience will be able to come up to this microphone, and then we'll also be taking questions live. So today we'll be talking about detection, asteroid detection, tracking, characterization, and mitigation. So we're going to start off to get anchored into the fundamental science part of asteroid, and we're fortunate to have Jim Zimbelman of the National Air and Space Museum, who is a planetary scientist here, and he is also the curator of Exploring the Planets. So, Jim?
So my role in this first part is to just introduce the idea that impacts are common throughout the solar system. The rest of the speakers are going to focus a bit more on why that's relevant to the Earth, but I want you to understand that this asteroid issue that we want to discuss today has been present throughout the solar system. And the pictures up there right now are the faces of the moon. On the left is the side that we're sort of used to seeing. This is a full moon view taken by amateur astronomer Tim Hunter. But on the right is a picture taken by a remote spacecraft back in the Apollo days of the side that we do not see. And it's actually as heavily bombarded as only the southern part of our visible face of the moon. All of those holes are the result of impacts of something. Asteroids, yes, maybe some comets come into play as well, but the important point is our moon has just been battered to pieces. This is a picture taken by the Apollo 11 crew while they were in orbit before they did their descent down to the lunar surface. And the main point of this picture is that there are just craters everywhere of different sizes. What generates a crater of a different size? It has to do with how big the impacting object is and how fast it was going when it hit. Both of those things can vary and make craters of different sizes. Now, this particular part of the moon is what scientists call saturated by craters. And what does that mean? If something came and impacted again, it would make a crater that would destroy just about as much crater visibility as it is creating. That sort of steady state is what we'll see throughout many things in the solar system. Here is a close-up of the center of one of the most prominent craters on the visible face of the moon. This is the hill that is in the very center of the crater. And I'll go ahead and advance to the top view that just showed up is a picture from orbit of that crater. It's about 85 kilometers in diameter, has rays, which is material thrown out from it that go over almost all of the visible face of the sun. So the red dot on our full moon view is where the crater is, and those bright streaks are material that was ejected by that crater. So the hill is a rebound of the floor sort of bouncing back from the shock of the impact. Now, there are craters of all different sizes, and you maybe can't read the bottoms, but they are increasing sizes from something smaller than a grain of sand on the left to larger and larger craters around the moon, up to things that we call basins, something that is so big that it is almost hard to see as an individual crater. Well, that was the moon, at the same distance from the sun as the moon is us. And hopefully you guys remember, not too long ago, over the city in Russia called Chelyabinsk, there was an explosion in the atmosphere. Now, this was a video dash cam picture. And maybe some of you guys are used to the idea of videos in your cars. Well, it turns out to be really popular in Russia. One of the surprises is the reason is insurance coverage is so bad that they need video records of accidents. So there are thousands of these cameras scattered in Russian cities, and many of them captured the views of this object. So here's the cloud that was left by this thing as it streaked into our atmosphere and did not hit, it disrupted in the atmosphere. And this beautiful cloud unfortunately drew many people out onto the street. About 2 minutes after the impact event, the shock wave of its passage through the atmosphere hit the city, busted glass, all over the place. This is the entry to one of their large theaters. This is now one of the largest casualty rates of an impact event simply because of breaking glass that hurt people that were out on the streets because of hearing something had happened, but the shock wave hadn't reached the city yet. Well, as Cheryl mentioned, the reason we are celebrating Asteroid Day today goes back to 1908 on this same date. One of these same kind of events happened over a very unpopulated part of the Siberian tundra. And that blast knocked down the forest over a large area. There were several scientists who tried to get there. It was so difficult to get there, it actually took years for the scientists to make it. When they got to the location, they were going to look for a crater, but again, this exploded in the air, and the blast wave knocked trees down, like in the upper left, but right under the place where the detonation happened, the trees are still standing. All of their branches and leaves are stripped off, but it looked like a telephone pole forest. Well, these air blasts are something that we still need to think about. On the left are views from Venus. These are radar images, but they show the effects of this shock wave in an atmosphere. The object has been disrupted by entering the atmosphere, but the blast reaches the surface. And what we don't want to happen is one of those occurrences over a city. On the right is an artist's view of what if one of these air blasts happened right over a major city like Los Angeles. That is a concern that even without creating a hole in the ground, we need to be worried about these objects. Now, one of the most famous places, at least here in the US, to visit the result of an impact is something called Meteor Crater in Arizona. It's one of the youngest features preserved here on the Earth. Why doesn't the Earth look like the moon with all of those craters? We think that the same barrage happened, but Earth's geology and its active weathering system has erased many of those things. This feature happened about 40 or so thousand years ago, and that is young enough that it has not been erased by erosion and is now the site of a lot of public visiting, but also scientists. I went there when I was a graduate student to learn about impact cratering. Now, a little bit closer to home, for those of you who are from the DC area, you might not realize it, but a very large impact crater is not that far away. The map shows the two rims of this crater centered around the Chesapeake Bay. And so we refer to it as the Chesapeake Bay Impact. But surprisingly, this happened when this part of the continent was underwater. So let's go ahead and go forward. That colored map shows where the shoreline was. That white line is where the ocean front was 13 million years ago, and the impact was into the shallow continental shelf. Well, that actually was another contributor to a problem. So the diagrams are computer-generated views of what happens in these impacts. The upper left is only 5 seconds after the impact. Material is still being thrown out, and the light gray is water, the ocean water. The darker gray is the rock beneath it. 35 seconds after it, the center of the floor of the crater is rebounding, and that's what made the hill in the center of Tycho on the moon. So that rebound happens in less than a minute, and yet these features can be, the size of mountains. So this is geology on a very fast time scale. The lower diagrams show the water retreating from the impact, and then up to 5 minutes later, it finally came back and reoccupied the crater. And we don't see a crater today because it is about a kilometer beneath the surface of the ocean. And it's only through drill cores that we know that the crater is there. Now, an even bigger event, very similar to what I just described, happened over the Yucatan area of Mexico, and this led to the demise of the dinosaurs 65 million years ago. So the colorful map is gravity, looking at how the rocks are distributed in their densities, and those circular structures are the rings of this impact. This is a very large feature, but it also, just like the Chesapeake area, it impacted into a continental shelf. Unfortunately for the dinosaurs, it impacted into a carbonate rock. And without going into the great details of that, the impactor disrupted the carbonate and created an acid rain that contributed to the death and destruction brought on by this impact event. Fortunately, these size of impacts are pretty uncommon. And this one, 65 million years ago, should not happen for hundreds of millions of years. There have been even bigger impacts, though, in Earth's history. Giant is really not even the word to apply to this. The artist's view at the upper left is the early Earth and an object the size of Mars slammed into it and ejected much of the mantle of the Earth into orbit around the forming Earth. Well, scientists refer to this now as the Big Whack, informally, rather than the Big Bang. And our moon formed out of the material that was the result of this enormous impact. But it's so early that there is no geologic record of this on either the moon or the Earth now. Well, I'll move on to some asteroids, and you may not see them too well, but on the right side are some of the asteroids visited by spacecraft. On the left is a close-up view of one of the larger ones, because the spacecraft Dawn orbited this asteroid for a year, giving us information about it. And here's another view. This very odd-shaped asteroid is a result of an enormous impact. So the three views in the upper right, two are Hubble Space Telescope images, one of which is a mathematical model of the shape derived from those images, and then the colored view is the topography. That circular depression is an impact almost the size of the object itself. What that means is if the impactor had been even just a slightly bit bigger, it would have completely disrupted the asteroid. So impacts can not only make holes, if they are big enough, they can completely break up objects. Now, nature does impacts just fine on its own, but we as humans have done our own. Here is the Deep Impact mission, where an object was intentionally sent to impact onto a comet nucleus. And the lower right picture is a minute after the impact, so that a following spacecraft took pictures and spectra to give us compositional information of what was thrown out by that impact. So we are generating our own impacts now for the sake of science. And we do it in other ways. So when the astronauts went to the moon, the third stage that carried the astronauts out of Earth orbit towards the moon, for the first missions was just sent into orbit around the sun. Later on, this was the Apollo 14 third stage, was directed to impact the moon because the astronauts on previous landings had left seismographs. This caused the moon to ring like a bell and gave us very important controlled information about the structure of the moon. Now, even today, impacts are still happening, but we are fortunate to have actually witnessed a whole series of them in 1994 when a comet was busted up into several different fragments. So the picture at the bottom are what has been referred to as the string of pearls, all these little fragments of what had been a comet nucleus streaming towards Jupiter, and they make those dark spots that show up in the Hubble Space Telescope images of Jupiter. This didn't make a hole because Jupiter is a gaseous planet, but those spots remained visible for weeks. And I still remember, even though I was out of school, I had my own telescope, and I was just really impressed. I could see spots that hadn't been there the week before, and about 4 weeks later, I could no longer see them. So impacts are still occurring today throughout the solar system. Now, the moons of Jupiter have the whole complex history of their own. We'll just talk about a couple of them. The smallest there, Europa, is just a little bit smaller than our moon. Io is just a little bit bigger. But the two larger ones are mostly icy objects, and they have a very interesting record of impact on them. Ganymede, the biggest, is actually the largest moon in the solar system. And here is a picture from the Galileo spacecraft of one of those impact objects. Well, on this icy crust of Ganymede, there are some normal craters like we've seen on the moon, but what's that funny white spot? It has very little relief. Well, it's given the funny name palimpsest, which if any of you are historians, that refers to a process of writing where the actual ink of the writing is not preserved, but the impression of that writing stays on the paper underneath. That's called a palimpsest. Well, this is a crater that sort of relaxed. It went away, and yet it happened recently enough that we still have record of it in the icy crust of Ganymede. And its neighbor Callisto, only slightly smaller than Ganymede, has, again, even bigger impacts. The sort of white spot is a basin bigger than a single impact crater, and all of the white rings around it are the fractures in this icy crust caused by this very large impact. Jump back to Mercury. We've been sort of looking at the outer solar system. Well, the inner part of the solar system has been impacted just as much as the other things we've been talking about. This is a picture taken by a spacecraft named Messenger that was in orbit around Mercury for about 4 years, collecting a whole variety of interesting information. The bright feature towards the center of the scene, that's one of the more recent impacts. And it is bright because it has not weathered. Now, what do I mean by weather on a planet that has no atmosphere? One of the things that can alter the rocks on objects, particularly those without atmospheres, is the influence of the sun, either the particles coming off of the sun itself in the form of radiation or the gamma rays and sort of very high energy electromagnetic things. All of that can alter the soil and literally make it darker. So impacts are bright until this weathering process has dimmed the apparent brightness of these ejected materials. And we'll terminate here with Tethys. This is one of the moons of Saturn. So the whole range of the solar system has experienced impacts like we've been talking about. This is another icy moon, which means that its crust is completely made of frozen water ice. And the most prominent feature sort of at the upper half of the image there, that's an impact crater comparable to Tycho, like we talked about on the moon, a very prominent rim and a prominent central peak. Again, realize that that peak is the rebound of the crust after the impact, so that these size of craters literally take time to evolve. It's kind of hard to wrap your mind around, but the formation of that crater literally took minutes for the impact to occur, the crust to respond, and all of the ejected material to settle back on the ground. That sounds slow, but it's actually fast geologically. It's slow enough that if we had had a spacecraft out there orbiting, we could have observed this impact process. Well, with that, I'll open it up for questions. And we can either get them from the floor here. Yeah, and if you would please just go over to the microphone, and I'll try and repeat the question for the people online. We're going to start with a question that has come in on Facebook Live when we get the mic going here.
Good. Okay, we're going to start with a Facebook Live question from Ken. How big would an object have to be catastrophic on Earth?
Ooh, excellent question. How big does something have to be catastrophic? And that's sort of a complicated answer. Hopefully, the pictures I've shown you will help you realize if something hits the ground, that's a bad day right at that impact site. But we have also learned that if it blows up in the atmosphere, that can be a problem right beneath it. So what's the size difference? Let's just talk about Earth initially. Chelyabinsk and Tunguska, both were objects that disrupted in the atmosphere. Why did that happen? This was a rocky object. Why? How do we know that? There were little tiny beads of both of these things that were melted, that fell down to the surface, that have been collected, and they look just like meteorites, asteroid rocks. So that we know it was a rocky body, but it was coming in to denser and denser parts of the atmosphere. And just imagine pushing yourself, if you've been in a swimming pool, and the faster you go, the harder it is to push the water out of the way. At some point, you get low enough in the atmosphere that that pressure is so great, it literally blasts the rock apart. That's what makes air bursts. And I don't know if I told you, but Chelyabinsk was on the order of 20 meters. That's like 50 or 60 feet in diameter, the rock. Tunguska is more like 50 meters, so that's more like 180 or so feet in diameter. These are good-sized rocks, and they still disrupt in our atmosphere. If you get to something about 300 meters on that order, it's going to get all the way through our atmosphere, make a crater on the ground. I think the point of the question was what's catastrophic, and that you need a really big crater. So the one that did in the dinosaurs, the impacting object is estimated to be 10 kilometers, 6 miles in diameter. That made a crater in the Yucatan that was 180 kilometers in diameter, its outer ring. So a general rule of thumb is, and this depends on the speed of the object, about 10 times bigger than the object itself at normal impact velocities. That's the size hole that results if it makes it all the way to the ground. Just realize things blowing up in the atmosphere can also be a problem.
So if a meteor or asteroid were to hit Earth on the crust, depending on its size, what effects does it have besides the area near the asteroid?
Excellent question. What effects come from these impacts that do make it down to the ground? And one of the more interesting, at least to me, in aspects are earthquakes result. Not surprisingly, just like if you have a hammer and hit it on a bell and the bell rings, that is the result of the pressure on the bell, and that is propagated through it all. Well, that happens with the Earth too. So there are large earthquakes generated by these impact events. In fact, there are atmospheric pressure detectors. They measure the pressure of the Earth. The Tunguska event, way back in 1908, caused the atmosphere to shock. And it literally, this shock wave went around the Earth twice. Detectors both in England and some, I want to say in Asia, if I remember right, detected this pressure wave from the Tunguska air blast event twice. First when it was going around, then it circled around again, and another detection. So these waves that propagate either in the air or in the ground are going to make things that could be potentially bad. Now, there's a very interesting website that if you're really interested, when we're done, I'll give it to you. There's a little computer program where you can put in whatever size and velocity and kind of impactor you want, and it'll tell you what the results are. Things like acid rain, things like earthquake magnitudes, all of that can be determined depending on what inputs you put into that. So since I can't remember what the website is right offhand, just Google something like impact events on Earth, and I bet you will find the link to let you explore this on your own and put in all kinds of different things and see what would happen. Of course, kids love to put the biggest rock they can think of, and the numbers are just mind-boggling. It's hard to imagine. But play around with it, and that'll give you a better feel for what I've been trying to summarize for you.
Is there any way to predict or at least observe if there will be some kind of meteor coming to Earth?
Oh, is there any way to predict if these things are going to be happening? That's the rest of the presentations today. NASA obviously is very interested, but in fact many nations around the world are concerned about this, and Chelyabinsk just got people's attention. It isn't only the ones that hit the ground that we need to worry about. NASA has been involved, and our other speakers can give you more additional information, but to look for the initial charge Congress gave to NASA was to identify all of the orbiting objects that they could, big enough to, I want to say, 1 kilometer diameter. So that could potentially make like a 10-kilometer diameter crater. That's a bad thing. And NASA is well along in achieving that goal of finding those. We aren't ever going to find absolutely all of them, but we have over 95%, if I remember the number right, of these big guys. Well, Chelyabinsk has said we now need to go lower and look for the smaller objects. It's just the number of objects available goes up exponentially. The smaller you get, the more of them there are. And that search is still ongoing. And I think some of our other speakers will be able to give you a little bit additional information. This is on a lot of people's minds. Asteroid Day is evidence that not just the US or spacefaring nations, the UN recognizes this as an issue that we all need to worry about. And I think that's appropriate.
Is there speculation as to the body that caused the big whack?
Oh.
Identity.
What body caused the big whack? And there is speculation, lots of speculation. There is just very little evidence, unfortunately. And my understanding is the computer modeling to date is that that impact was so big that it has completely disrupted the impactor. Now, why do we even think that this happened? Well, these sort of debates only started with the Apollo samples. When we actually got moon rocks back, we realized that the composition, many different kinds of elements and their abundances and all of that, was very much like Earth's mantle. What is the mantle? That's lower down beneath our crust, the interior, the semi-liquid part of the Earth. How could you do that? Well, that's the answer, that an object knocked part of our mantle into orbit that reformed to make the moon. What kind of object is it? All that we know from the energy required to do that is it's something as big as Mars, which is half as big as the Earth. That's a very bad day. I mean, this happened early enough that even if there had been primitive life, it could have not survived the conditions that resulted from this. The estimates I've heard is this is within the first 10 million years of the 4.6 billion years of the Earth. So that very early, unfortunately, we don't have good answers other than the computer models that people are running right now. Yeah?
I have one small question. So how much time in advance should we find those big guys?
How much time will it take to complete that, sir?
No, how much time in advance should we find those guys in term so we can prevent catastrophic outcomes?
I didn't hear quite all of it.
So how much time in advance should we find those really big guys?
Gotcha. How much time ahead do we need? That's an excellent question to do something about it. Obviously, the bigger the objects are, we might have a longer period of time. It's just the little ones are an issue. I heard estimates that Chelyabinsk, if someone had been looking in the right place, would have been very hard to find that up to minutes before the impact. The bigger objects, we might find it days to weeks out. The biggest objects that we've got a pretty good survey now, we can months to maybe even years out. And to ease everybody's fears, the objects that NASA has been tracking, the big ones, none of them are on orbits that should be a problem in the foreseeable future, as I understand it. But the smaller ones and the ones that we keep finding and refining orbits, how long do we need? I don't know if we have the answer to that. Now, the NASA scientists are going to give you a lot of ideas of ways to mitigate this. I can tell you it's not going to be Bruce Willis and a drill team up there that's going to save the Earth. As interesting as that movie was to watch, completely wrong science. But you're going to hear the right science here in just a minute.
Thanks, Jim. Thanks very much. All right, well, Jim has given us a really good foundation about the science and the impact hazards throughout the solar system. So we're going to move on to our next topic and dive into the impact hazard from a human space perspective. So I'd like to invite Dr. Tom Jones to the stage. Tom is a 4-time astronaut with 3 spacewalks. He's a pilot for was a pilot for the Air Force, a planetary scientist, an author, a speaker, and he's also a chairman of the Association for Space Explorers Committee on Near-Earth Objects. Welcome, Tom.
Hi, everybody. Welcome to Asteroid Day. Let me thank Jim Zimbelman here for helping us set up with the Smithsonian this event here at the Air and Space Museum today. Wouldn't have been possible without his cooperation and those of his colleagues at the Air and Space Museum. Hello to everybody around the world watching on the Asteroid Day webcast. And I'd like to talk to you about my involvement with asteroids on a personal level, because astronauts have to live with asteroids and their fragments when they're up there exploring space. So we have a personal I guess, get-in-your-face kind of experience with asteroids that we worry about when we're in space. Small fragments of asteroids and comets can damage our spacecraft and do in a space mission, whether it's manned or unmanned. So let's talk about that in a little bit. I'm going to talk about my perspective on asteroids as experienced from an astronaut's life. Then we're going to talk about the global hazard that asteroids present to us here living as humans on Earth, and what the future of dealing with this hazard is through an international response around the globe. So, 50 years ago, we were orbiting the moon for the first time, and of course next year is the 50th anniversary of the first moon landing. We had astronauts circling and then walking on the moon, and of course they saw, just like Jim showed you, this pockmarked, cratered surface of the moon firsthand from only 100 miles or even 60 miles up as they orbited the moon. So astronauts got to see this geological process of cosmic bombardment as they performed their lunar exploration missions, of course. So I didn't get to go to the moon. I came along a generation after that. But as a planetary scientist, I got to learn about the process of impact and learn what the Apollo astronauts saw and then what's going on our home planet. Now, if you were an Apollo astronaut, you would drive around on the surface of the moon in your lunar rover. This is Apollo 17, and you can see on the far left there one of the astronauts standing by the lunar rover, and then the lower corner, the shadow of an astronaut taking this panorama of Shorty Crater. It's about 100 meters across. The astronauts explored these craters because not only did they tell us about the process of forming craters from asteroid and comet impacts, but they excavated material from beneath the surface of the moon, brought it to the surface, and the astronauts could then pick up those rocks, tell us about what the interior of the moon was made of, thanks to these craters doing the digging for us. Now, back in the inner solar system here, we have a map of the orbiting planets, Mars, Earth, Venus, and Mercury towards the sun at the center. And you see all those little dots inside the green belt of the main asteroid belt beyond Mars. The little dots at the center of this screen are the near-Earth asteroids that get kicked out of the big asteroid belt by Jupiter's gravity and some collisions. They wind up in the inner solar system close to the Earth's orbit. And that's the hazard that we face as humans today, these near-Earth asteroids, Earth-approaching asteroids, we call them. Here's an example of one zinging by the Earth back last October. This asteroid 2012 TC4, it's about 10 meters across. And it was zinging by in the camera here. You can see it going through the star field. It missed the Earth by about 50,000 kilometers, about 30,000 miles. Just an example of one of those small near-Earth asteroids coming by the Earth. This is a frequent occurrence, happens all the time. Our telescopes pick up some of them. A lot of them are undiscovered. And of course, those are the ones we worry about, the ones we don't know about that can smack into the Earth without warning today. Here's an artist's conception of that same asteroid as it whizzes by the Earth on its orbit around the sun. This one came, as I said, about 30,000 miles from the Earth, well inside the orbit of the moon. Now, when I was up on the space station, on the space shuttle, I had this personal experience of being in space. I think the peak moment of my mission experience was doing spacewalks at the International Space Station back in 2001. On the date of one of my spacewalks, February 12th, we actually had the first asteroid landing by any man-made object. Okay, so the near Shoemaker spacecraft touched down on the asteroid Eros. You see it at the upper right corner. And in the artist's conception at the lower right, you see that spacecraft settling onto the surface of near Shoemaker, or the asteroid Eros, the near Shoemaker spacecraft on Eros. And I happened to be doing a spacewalk while this was occurring. And while the spacewalk was great, building the space station was very satisfying, I thought to myself, wouldn't it be cool to actually do a spacewalk on an asteroid in the future? So later in the talk, I'm going to mention the asteroid exploration possibilities presented to us as explorers and how we can use those asteroids to extend our reach farther into the solar system. But while you're exploring space, building the space station, flying on the shuttle for science, for example, you look down into our atmosphere from 200 miles up, let's say, and you see these pieces of asteroid debris, small asteroids, if you will, burning up in the atmosphere below us. And that's really a mind-blowing experience in the sense that you realize that you're now exposed to this cosmic hazard where the Earth's atmosphere isn't there to protect you. And you have to worry about those effects on your spacecraft. Inside the space shuttle, when I was working up there, we had those windows above my head that you see in the scene here. triple paned windows, 3 thick panes of quartz glass to protect us from impacts that might occur, to make sure that one asteroid fragment couldn't blow through a single pane of glass and depressurize our craft. We actually saw on our window surfaces at the end of a 2-week mission, there would be pits in the windows from small impacts, either natural debris from asteroids and comets or maybe man-made ships of space junk circling the planet. So you see the window at the center with the pit in it, about the size of a pencil point, and then a blow-up or an enlarged view of that crater in the window glass on the upper left. And spacecraft designers have to deal with the asteroid hazard as they plan for longer missions in space. The space station up there, you see this great model of the space station over my shoulder. The laboratory that my crew delivered to the space station is armored with debris shields that protect us from small pieces of asteroid, comet, or man-made debris. And that waffle-shaped panel that you see there running up and down the Destiny, those are debris panels or debris shields meant to break up and slow down asteroid debris or man-made debris as it penetrates the spacecraft. And so far, we haven't had any dangerous impacts on the space station, but as you see on the solar panels here on the space station, we have sustained strikes from either space junk or natural debris. There's an impact at the center that's actually shattered one of the solar panel sections on the International Space Station, and we have to plan for resisting the impacts and then repairing the damage that might occur on a mission to the space station or on a mission to Mars in the future. Now, as I look down from the space shuttle and the space station, I got to look as a planetary scientist on these impact scars around the world. One of the biggest ones that still exists on the Earth is this one called Vredefort, about 2 billion years old, 300 kilometers in diameter in South Africa. And this is one of the big multi-ringed basins that we see constantly on the moon and the other moons of the solar system, the other planets. This is a big multi-ringed basin that we see on the Earth. In North Africa, one of my space missions carried a radar laboratory that could image beneath the sands of the Sahara. And in Chad, we saw the Arunga crater. It's only about 13 kilometers across, but that would do a real number on the human population in that zone. This one's buried beneath the sands, and the radar aboard the shuttle revealed its contours to us. And then a very famous astronaut landmark as we circle the Earth is to see this one, Manicouagan, up in Canada. It's in the old rocks of the Canadian Shield, and it dates back to about 200 million years ago. And it's a scar that's been heavily eroded by glaciers over the periods of the ice ages, but now we can still see that frozen lake outlining the crater's rim for us in Canada. And as Jim mentioned, the freshest, probably most famous impact crater today on the Earth is Barringer Crater or Meteor Crater in Arizona. Who's been to Meteor Crater? Raise your hand. Okay, about half a dozen of us. The rest of you are in for a treat. I urge you to go there on your next trip to the Grand Canyon area. That's Flagstaff, Arizona, off in the distance. There's Meteor Crater. And as a planetary scientist, I have been able to go on field trips with other students down there, exploring the interior of the crater, learning about the impact process. And then it reminds us that this is going on today on our planet. The Earth is still subject to this cosmic bombardment. Geologists today know of about 190 impact craters around the world. There have been many more throughout the 4.5 billion year history of the Earth, but they've all been eroded or destroyed as the plate tectonics and erosion changes and alters the face of the Earth. Now, this is a nice chart that I like. Our NASA friends, Kelly and Lindley here, furnished this for us. This is the fireball record seen from Earth orbiting satellites looking down at our atmosphere, and it records the constant rain of cosmic debris into our atmosphere, pieces of comets and asteroids. The bigger the energy, the bigger the circle. As you see from the scale, the red dot over Siberia, that's Chelyabinsk in 2013. That one was about half a megaton in explosive energy. And of course, the smaller fireballs are going on constantly. If you were awake at night out in the middle of the ocean, you'd have a better chance of seeing it than if you were in your bed at night with your eyes closed. We don't see a lot of these fireballs personally, but they happen around the globe. Here's an example of one filmed in Arizona in 2016 on a dash cam. You can see the fireball lighting up the horizon there. That really got the attention of these late night drivers. And in Arizona, several security cameras filmed this event as well. It was probably about the size of a basketball or maybe something the size of a trash can burning up in the atmosphere. But as it incinerated and grew incandescent, it lit up the entire landscape. Here's one more last scene of that Arizona meteor. Now, no harm to us on the ground. This couldn't make it down through the atmosphere. It has to be about 40 meters or so in diameter before it makes it down to the Earth's surface, going the wrong way. Here's the South African impact that occurred back in just June 2nd. This was an asteroid, 2018 LA, I believe it's called. Let's see if I can recycle to this one. One more. Here we go. And here it's live now. There's the Fireball 2018 LA. It was a small asteroid, only about 3 meters across, just the size of this stage or less. And it was detected by NASA's search programs about 8.5 hours before impact. They predicted it was going to land in South Africa, and sure enough, observers down there saw this asteroid burning up in the atmosphere. Someday we might learn whether actual meteorites fell out of that and were recovered on the ground. But it's a reminder that we're constantly being rained on by pieces of asteroids or comets. We've talked about Chelyabinsk, the one that occurred in 2013 and blew up over Russia. That's the small asteroid down there on the 50-yard line, to give you a sense of the scale here. But that same day in 2013, another asteroid, 2012 DA14, came whizzing by the Earth. That one was predicted. It was about 40 meters across. Had it struck the Earth, it would have caused widespread damage. Fortunately, we knew the path of this one very precisely, and it missed the Earth by ample margin. But those are the kinds of asteroids that we're discovering constantly. Kelly and Lindley are going to tell you about their discovery programs funded by NASA, and the job for us is to find enough of them soon enough that we can take action to deal with this hazard. Because here you see the dinosaurs having a conversation. Now's the time to develop the technology to deflect an asteroid, and of course, they didn't have a space program. They were left out to lunch when they were struck by the Chicxulub object 66 million years ago. This is a global hazard. Folks, it needs a global response, and that's Asteroid Day's mission, is to get everybody around the globe involved in knowing about the asteroid hazard and then helping their space agencies and countries and governments around the world to work together to respond to this. Now, I mentioned the 2018 LA impact, that little fireball that we just saw in South Africa. The initial discovery of that 8 hours earlier resulted in a prediction of that blue line across the globe. It was going to land somewhere along that line. And then as the orbit got more refined with better observations, scientists zeroed in on where it was going to hit in South Africa. So we were struck by this diagram showing that many countries could have been affected by this impact. Had it been a larger one, it would have really got a lot of people's attention, trying to evacuate perhaps the danger zone down below. And here's another diagram of the path of that small asteroid, again, just the size of this stage, coming in and eventually burning up over South Africa. It's a global hazard because it affects many regions around the world as we learn about, track these asteroids, and then refine the impact point. So here's a notional diagram. If the asteroid was going to land on one of those red spots, that would be very bad. If it landed in the ocean, it was big enough, bigger than 40 meters, it might create a tidal wave or a tsunami out in the ocean and damage the shorelines nearby. If it landed on land, it could do in a city or a part of the Earth's population in a region around the world. So if you're an asteroid defense expert, you're going to try to move the orbit of that asteroid so it misses the Earth left or right entirely, so we get to a good result, safety for the Earth. But in the process of moving that asteroid across its path from one target zone to the next until it misses the Earth entirely, it's going to involve multiple countries, as you can see here. And so our challenge internationally is to work together so that we agree on whether we're going to drag it to the left and make it miss the Earth, or whether we're going to drag it to the right across Europe in this example and make it miss the Earth. We have to have international buy-in, cooperation, to make sure that our plan is agreed to by all of the countries that might be affected by this decision. That's where the United Nations comes into this process. Now, I'm a member of the Association of Space Explorers, the Astronauts Professional Society. We have been able to sit in on the conversations at the United Nations, along with the space agencies like NASA, along with their partner space agencies, along with the member states around the world. We turned in a report back in 2009 that suggested some ways we might deal with this global hazard, and it led to the adoption by the UN of these two groups, the International Asteroid Warning Network, to share asteroid tracking and warning information, and then the Space Missions Planning Advisory Group is the group with NASA and the other space agencies that's working on plans to deflect a dangerous asteroid away from the Earth in the future. So a couple of our suggestions made it through the mill at the UN and got worked into the current international response to this hazard, and that work is ongoing thanks to NASA's leadership and the other space agencies that work with NASA. We've been at the UN. I'm seated here speaking to the United Nations Committee on the Peaceful Uses of Outer Space, talking about what we can do to work together to prevent an asteroid hazard. In the Association of Space Explorers, we're going to stay involved in this process because as space travelers, space explorers, we can see internationally the need for this cooperation, just as the space agencies do in working on this really interesting and also difficult, challenging problem. Two things that I would leave us with that we have to do next, working together around the globe. Number one, we have to search for those dangerous undiscovered asteroids that might threaten the planet. And NASA's been doing a great job with their asteroid discovery programs. We're going to hear the details of that in a minute. But we have to get better at discovering asteroids. One way to do that is perhaps to fly an infrared telescope. This one's called the NEOCAM that NASA has proposed. It can search for the smaller asteroids that our ground-based telescopes can't detect. And so that telescope, in about 10 years, if funded, could fly and detect and catalog the asteroids that might be headed our way. We would learn about a large fraction of those that could destroy a multi-state region, for example, in our country here in the United States. And a second thing that we should do is to conduct a demonstration of our space technologies so that we can actually assure ourselves that with our space skills we can ward off a hazardous asteroid. And you're going to hear about this from Cheryl Reed, our moderator, the DART mission, which is planned in 2022 to smack into a harmless asteroid and actually measurably change the orbit of that object to demonstrate that we can apply our space skills in defending planet Earth. That's a very important confidence-building test that we need to apply in our efforts to avoid a future catastrophic collision with an asteroid. Now let me just turn to wrap up here with the possibilities that asteroids present us for exploration. This is a close-up image of the asteroid Itokawa taken by the Japanese spacecraft Hayabusa back in the 2000s, around 2005. And this close-up, you can see it's only about 6 feet across in that bar on the lower right corner, and the car is just plugged in there for scale. But what a fascinating place to walk around or float around if you're an astronaut explorer, to actually understand the surfaces, the processes that create the surfaces of these bodies, learn what resources are up there so we can use them in future space exploration. We have meteorite samples right across the mall at the Natural History Museum. You can see their fantastic meteorite collection. Some of the materials on asteroids are valuable to us as space explorers. The lower left meteorite, Murchison, the one in the upper left, Tagish Lake, are rich in water. So we can extract the water from these bodies with robots. Astronauts can help if they need to. And then we can use the water to make rocket fuel, create the oxygen you need to breathe, drinking water for astronauts, of course, and their outposts in space. So the resources from the asteroids, meteorites representing samples of them, can help us get to Mars someday at lower cost with greater safety. And I hope that this search for resources in space will lead to a growing economy based on asteroid mining in the space between the Earth and the Moon. Visit the nearby asteroid, ship the products back for incorporation into our space economy, and then eventually for our expeditions into the rest of the solar system. That's the promise of asteroids. We can turn a hazard into an opportunity if we do our tracking, our discovery, our cataloging, and then our space missions to these small bodies. So to wrap up, let me close with a couple of final points. Asteroids, near-Earth objects, are a long-term hazard to our civilization. If we sit back and do nothing, we'll go the way of the dinosaurs. Space exploration gives us the means to prevent that from happening and to help us preserve our species for the long run. So the big open question is, we have the know-how to stop an asteroid from hitting the Earth. Do we have the will working together? And that's our challenge on Asteroid Day and every day of the year, is to work together to solve this problem of stopping the asteroid hazard from affecting humanity on Earth. So with that, I thank you very much, and let's go to some questions for a few minutes. Anybody have a question, come right up to the mic, or we'll take some live from Facebook and from around the Asteroid Day community.
So we're going to start from a Facebook Live question from William. Have they found a better way to detect these asteroids coming from the sun?
Oh, so the question is, can we detect asteroids coming from the sun in a better way? You know, our ground-based telescopes work at night. During the daytime, the glare from the sun wipes out their detectors. They're not able to see asteroids in the daytime sky. Asteroids by themselves are very dim, hard to detect. So we have that hole in our ability to search for asteroids at present. That's where the space-based detectors come in, because they don't have to worry about the daytime sky. They're outside the atmosphere. Their infrared detectors work almost all around the sky except very close to the sun. So we can hope that future space-based detections of asteroids will be the way to solve that problem of asteroids coming towards us in our blind side.
Where do most asteroids come from, and how are they blown towards Earth?
Okay, so where are the asteroids, where do they come from, and how do they get headed towards Earth? Well, they are the leftovers. Asteroids and comets are the leftovers of the formation of the planets 4.5 to 4.6 billion years ago. When we've dated the meteorites in our collections, we know that they're that old. They're older than any rock on Earth. They date to the birth of the solar system. So they're the raw materials that formed the planets, and the leftovers are still circling the sun in the big asteroid belt between Mars and Jupiter. Now, they're very happy in their orbits around the sun in between Mars and Jupiter. That asteroid belt gets affected, though, by the giant planet Jupiter's gravity. And so what happens is Jupiter's repeated gravitational tugs on the asteroids in certain spots in the belt causes their orbits to change, and they get thrown into the inner solar system. Sometimes the asteroids collide with each other, and those fragments get thrown into the inner solar system as well. So those become the near-Earth asteroids, of which there are millions, and those are the ones that cross or approach the Earth's orbit and present a hazard to us. Eventually, they get either run into by a planet, or they get burned up in the sun, or they get tossed out by a planet's gravity into the interstellar space. So they're not a permanent population, but Jupiter keeps pumping them in towards us, and that's why this process has gone on for 4.5 billion years.
So we're going to take another Facebook Live question from Sandesh. Any new element unearthed from these asteroid craters?
Have we found any new elements on Earth from these asteroid craters or the meteorites? That's a great question for a meteorite expert, and I don't think I recall that we've found any new elements, certainly, and maybe some new minerals. Yes, I think we have found new minerals, new combinations of elements in asteroid fragments, meteorites, that we've discovered on Earth. So I don't think any of them are commercially valuable. For example, we found diamonds in meteorites, but we find them on Earth too. So it's not worth going into space to mine diamonds. We already have them here on the ground. We don't go into space to mine water from the asteroids to bring the water back to Earth. This is a water planet. But in space, water is gold. And so we can use the water we discover in space to use in space and lower the cost of having to haul rocket fuel and water up from the ground at great expense.
Another Facebook Live question from Doris. What is causing the changes that create the solar system impacts, and can this residue impact Earth?
So I think, as I understand it, it's a repeat of the question I had earlier about where the asteroids, where are they coming from towards the Earth?
And their residue.
Okay, so I'll take a different tack on it this way. So we have this population of asteroids, the near-Earth asteroids, that are spun into the inner solar system constantly by the influence of Jupiter's gravity, collisions, and so forth. So what happens to those asteroids is, as the Earth goes around the sun, we encounter some of them in their orbits. Now, some of those asteroid orbits are very elongated. They plunge close to the sun, go all the way out past the orbit of Mars and back into the inner solar system. And then as the Earth goes around in its almost circular orbit, we encounter those orbits. Then we get run into by asteroids that are very close in their orbits to the Earth's orbit. So they almost fly in formation with us around the edges of our orbit. And those are particularly tough to see if they're on the daytime side of the Earth as they orbit the sun. So this cosmic debris from the formation of the solar system continues to present us with a problem. And that's what we're talking about today, the hazard from asteroids, how we solve that internationally to prevent humans from experiencing a catastrophe on the scale of that did in the dinosaurs. NASA is going to tell you today about how successful they've been with their search programs. We have a lot of undiscovered asteroids that we still have to find. For example, the ones like Chelyabinsk that can destroy an entire city happened in 2013, 20 meters across, only about half the size of this room. That could have destroyed an entire city had it come in more steeply or a little bit faster. So we have to find even those smaller objects that can't destroy civilization but could wipe out a metropolitan area. Okay, I think that wraps it for me. Thanks for that. We're going to turn it back over to Cheryl and then our NASA speakers.
Thanks, Tom. All right, super cool stuff. So defending planet Earth is a 24/7, 365-day-a-year job. And our Congress has commissioned NASA to be the overseer, to be the planetary defense coordination function for the U.S. and to work globally with all of the nations around the world to support this very important effort of planetary defense. So I'm going to invite the planetary defense team up here. We have Lindley Johnson, who has been with NASA since 2003. Formerly, Lindley was a lieutenant colonel in the U.S. Air Force, 23 years of service. He's an astronomer. He's also the Planetary Defense Coordination Officer for the Planetary Defense Coordination Office. Welcome, Lindley. And let's invite Kelly Fast. Kelly is, for NASA, the Near-Earth Object Observation Program Manager and Program Scientist. She also is an astronomer, a planetary scientist, and has been working for NASA since 1993. So this is the team, this is our leadership team that worked very hard to keep us safe. So we're going to hear from them now. Thank you.
Thank you, Cheryl. Get a slide up here. Okay. Yeah, I'm Lindley Johnson. I'm the real-life Bruce Willis. Try not to look disappointed. So I and Kelly are going to tell you what our program is at NASA, what NASA is doing, working with the world community on this problem of asteroids that could impact the Earth. So, Planetary Defense Coordination Office, in a good government office, we have a mission statement, and this is ours. The office was created in January of 2016, and we lead all the activities that NASA and our nation does to coordinate both in the U.S., interagency, across the departments and agencies of the U.S. government, and also with international efforts to address the hazard of asteroids in near Earth space. So we lead in our efforts to detect any potential impact that could do significant damage at the Earth's surface, be able to, once that object is detected and we've tracked it, to appraise what the effects of an impact by that object might be so that we can inform the government and our decision makers as to what might need to be done, and also work to develop strategies that the U.S. government would use to respond to the threat. So the first thing we have to do is find him. And I saw Superman around here a little while ago. Where did he go? But I want to turn it over to my colleague, Wonder Woman, Kelly Fast, for the Near Earth Object Contribution Program.
Oh, you're doing it
I'll write it for you, okay.
Yes, because you've heard all this introduction and you're thinking in your mind, so now what? So now what? Well, the first order of business is to find them, and so that's very important, and it's something that NASA is tasked with and our partners around the world, and so place a great deal of importance on that. And so we have programs that fund efforts to find them. And the way you do it is you look up, you use telescopes to find these objects, asteroids and comets that could pose a hazard to Earth. And so at NASA, some of our primary assets that are used in the search to find them to begin with is the Catalina Sky Survey, which has a couple of telescopes in Arizona, and the Pan-STARRS survey, which has a couple of telescopes in Hawaii, and the two of those together are responsible in recent years for the bulk of the discoveries of unknown asteroids that are now known and cataloged and continue to be followed up. Also, in addition to that, there's a couple of other telescopes in Hawaii, the Atlas telescopes, that try to look for maybe those objects that are closer to the Earth that maybe fell through the cracks to catch that before something might become a problem. In addition, we've got something in space, the NEOWISE survey, which is actually a repurposed astrophysics mission called the Wide Infrared Survey Explorer. And so it wasn't designed to search for near-Earth asteroids, but asteroids will photobomb wherever you're looking in space. They'll move through that starry background, and so this telescope in space can look for asteroids as part of its extended mission. Even though it's not optimized to do that, it's able to at least get information, because it's looking in the infrared, on sizes and on characteristics of asteroids. So it's been very valuable with making some new discoveries, but also finding out more about what these things are made of. And finally, there's the Space Surveillance Telescope, which is an Air Force asset, which had been used in New Mexico and is in the process of moving to Australia. It has a space situational awareness activity, but as part of that, again, asteroids, vermin of the solar system, they're going to photobomb anything. Some of that information can come from that asset as well. Gives us some coverage in the southern hemisphere and the southern skies, which is great. Okay, moving on. But the thing is, the fantastic thing is there's partners and astronomers all over the world who are part of the search and follow-up. And even though a lot of the surveys funded at NASA are the ones that are providing the bulk of the discoveries, then folks around the world will go and get more observations, because it doesn't help just to see an asteroid. You need to observe it enough so that you can figure out where it's been and where it's going in the future, and that's how you're going to know, is it going to be a problem here or not? And so there are observations all over the world as part of the International Asteroid Warning Network that was mentioned earlier, and beyond. And so, speaking of the International Asteroid Warning Network, which Lindley was highly involved in helping to stand up also, these are some of the signatories who have said, we have assets and we will bring them to the table should something, should there be an issue, and we have space agencies and organizations and even an amateur astronomer from around the world who've signed on to this to bring their assets to bear in the search and follow-up. Now, what do you do with all of those observations? You have to somehow pull this together and make something of it. So all of the positional observations from all of the telescopes all over the world are sent to the Minor Planet Center, which is also now fully funded by the Near Earth Object Observations Program at NASA. And they receive all of those positional measurements for small bodies, not just near Earth asteroids, but main belt asteroids, Kuiper belt objects, comets, everything, all small bodies in the solar system, all those bodies moving around. And they're responsible for the initial designation. They do an orbit determination, and they are now operating as part of NASA's Planetary Data System Small Bodies node. But in addition to that, there's the Center for Near Earth Object Studies out at JPL in California. And that organization takes all of those measurements and does precision orbit calculation, and they look way out into the future to determine if something could pose an impact threat in the future, and also looking for something that was maybe just discovered to do a quick analysis to see, is this something we need to worry about right now? So they have some systems both to look at that short-term and that long-term situation for anything that's been discovered. And should something become an impact threat, they will do the calculations to try to determine where that position might be. And Tom showed earlier that's something that was calculated by the CNEO's group out there to show where that asteroid 2018 LA might impact over that swath over Africa and over the oceans, and it eventually zeroed into, with additional observations, a swath over Botswana, and sure enough, that's where it came in. So that was a good dress rehearsal, actually, for our whole system around the world. And so it was good to have that. It was nice. It was something very small, but it helps us be ready for something in the future. Okay, so then, Lindley, how many have we found?
Well, Kelly, this chart depicts the number of asteroids of all sizes that come near Earth that our projects have found over the years. As we mentioned, our program began in 1998. So we've now been searching for this population of asteroids for 20 years. But you start to see when our program started back there in 98, a bump up in the number of objects discovered, and that's due to NASA's program. And as we've improved our capabilities, brought on more observatories to find these objects, you see the increases in rates of discovery. On that bar chart, what's in green, these are all the discoveries by our Catalina Sky Survey that Kelly talked about. And then in the purple, Pan-STARRS survey was brought on in 2011 and started making discoveries, and you see how they have added to the overall count in our catalog. So last year in 2017, we reached an all-new record of over 2,000 near-Earth asteroids discovered, 2,057. So far this year, we have discovered 882 of all sizes. We're a little behind the curve from last year. That's due to some bad weather in Hawaii that has occurred through the springtime. And so we're a little bit behind, and so whether we'll be able to break that previous record in 2017 this year, we'll have to see. If we get good weather in the fall, maybe we will. This is our total accumulation of objects discovered. Depicted by the red are the 1 kilometer and larger asteroids. That was our original charge from Congress, is to find those 1 kilometer and larger, because that would impact by one of those would be have global effects, be a very bad day for the whole world. So you see the discovery rate for those was pretty active in the early part of last decade, but now it's leveled off. And that means that we have found most of that population. We are still finding one every other month or so, so we're still adding to that. According to our population model, we believe there's about 30 or 40 more of them out there to be found. but we've already achieved the objective of finding over 90% of that population. Our current charge is to find 140 meter and larger population, and that's depicted in the orange. And so you see the steep discovery rate of those and adding to the catalog. But most of the catalog now are objects smaller than that size. And even though those aren't as severe a threat to populations should they impact, you did see in some of the earlier presentations an airburst by an object that size, what could happen. So our total catalog now is over 18,335 as of the 24th, which was about a week ago. And then we've shown listed what of that population we consider the potentially hazardous asteroids. And these are the population that their orbits come close enough to the Earth that we really need to keep an eye on them, because over time their orbits could wander into a collision course with Earth. So there's almost 2,000 that we monitor a little closer, of which 155 are larger than 1 kilometer. There's also 107 comets that come into the inner solar system and that we're charged to keep track of.
Okay, so that's wonderful, wonderful. We're finding them, but how many have we not found? And that's something that that's the big question, because what we don't know about is what would worry us. And so this chart here gives an idea of where we stand. That red line that travels up the plot there represents the estimated population of objects. So the number of objects, the smaller ones, based on what we see, can try to estimate what we can't see. There's folks who do some serious modeling effort on this. And so that red line represents what we expect is out there. And those green bars represent the number found. And so the large objects toward the right side of that plot, you'll see it's pretty much filled in. And so that blue line kind of shows how complete we are. These are based on models, and there's some issues with when you're trying to estimate just a few of a particular asteroid. So that's why there's a little bit of a jagged line in the completeness. But the bottom line is that of the large objects, they're easier to find, had some time to do it, not finding them as quickly anymore. And so a lot of that population is pretty nailed down. It's the smaller objects. And what Congress has tasked NASA with finding are the objects down to 140 meters in size, 140 meters in size and larger. And this comes from folks doing models of impact effects and trying to determine what are the ones that we really need to worry about. Okay, great, we've pretty much nailed down the 1 kilometer and larger objects. Now what should we worry about? And down to that size is where you could have a regional effects if one of those were to hit the Earth. Yes, the smaller ones too, we want to look for, and it's not like you're not going to see them if they're close enough to see them and you're looking with your survey telescopes, but those other larger objects, that's what we're pushing for, because that's what we've been tasked with Congress to do, and we still have a ways to go. And so another way to look at it, a little complicated pie charts, but our progress since 2010, these different colors represent those different size groups that were shown earlier on the other plot. The bottom line here, let me just say, is the white area of all the 140 meter and larger objects. All the white space on the pie chart represents what hasn't been found. And so from 2010 to 2018, from left to right there, you'll see that some of that has been filled in, especially with the larger objects, the 1 kilometer and larger, the red. Okay, great, we're in much better shape there, filled a lot of that in. And the yellow there, okay, we've grown that part of the pie for the 0.3 to 1 kilometer and larger, or 0.3 to 1 kilometer objects. Grown the pie. There's still a ways to go. 140 meter to 300 meter, that range. We've made progress over the past 8 years. The folks doing the work, boots on the ground, have really made progress, but there's still more to be done. So then, that's great. So how do we learn more about the ones that we found? Okay, I'm going to keep going with this. You find them, but you want to know, what are they made of? Because it can make a difference if something were to become an impact threat. Is it kind of a rocky, fluffy, icy even object? Is it a metallic, dense object? Is it going to make it through the atmosphere? Is it going to not make it through the atmosphere? That's something that's important. So it's trying to study the characteristics. And so those telescopes we talked about earlier were search telescopes. These are ones that actually are used to study the properties of asteroids and other astronomical objects. And so NASA actually has a telescope in Hawaii on the Big Island on Mauna Kea, the NASA Infrared Telescope Facility, and it studies asteroids in the infrared to learn about their characterization, take spectra, look at the light that we can't see with our eyes, and learn something about what they're made of from those observations. Radar is very powerful. You hear radar and sometimes you might think search because it's used at airports and all, but you can't use that to search for asteroids. Just don't have the power to do that. But once you know where to point that radar, if you know exactly where to point that radar, you can study asteroids and get some amazing images, radar imagery of what the shapes are. And you can really, really nail down the orbits once you can put radar on them. And then finally, there's another telescope that's kind of getting in the later part of its mission life, the Spitzer Infrared Space Telescope, that has been incredibly productive. And there are folks in the asteroid community who propose for time on that telescope and get information on asteroid characteristics using that. But why don't you take this, talking about what we get back from.
Well, these are some of the images that our ground-based radar, interplanetary radar, are able to take of these objects. This was a large asteroid, a kilometer in size, that passed close to Earth back in earlier in 2017. And if they come close enough, the radar return, we can process those returns in such a manner that we're able to determine the shape and size of the object. And so you see a collage of images there on the left from the Goldstone radar, NASA's Deep Space Network Goldstone radar. And on the right is a single image, composite image that was developed by the Arecibo radar capability, the Arecibo Observatory down in Puerto Rico. On the lower right there, you see what Kelly just talked about, the type of spectroscopic information we get from the infrared telescope facility in Hawaii, that those little squiggles of lines at the various wavelengths tell us what the composition may be of the object. Another large object that passed by the Earth close enough for radar last year was Florence. Now, Florence was discovered way back in the 1980s, well before our program started, but this was the first time it had come close enough to the Earth that we could get radar on it. And in that observations of it, we discovered this asteroid had two small moons surrounding it, orbiting it. And so these asteroids are miniature systems in themselves of planetary science. And so these little worlds are out there for us to not only be aware of and determine if there are any impact threat to the Earth, but there are also destinations for exploration, possible resources for the future, and places that humans will eventually go. One more image of an object that was found by the NEOWISE satellite, the one that Kelly mentioned that got turned over by the astrophysics department, and we turned it into an asteroid hunter. It was discovered by NEOWISE, the orbit was determined, and then we were able to get the radar on it. And so you see kind of an unusual shape of what some of these objects are. We're always anxious to see these radar images come in because we never know what we're really going to see because they're not round like planets are at this size. They are composites of rock that have been stuck together. I'm going to let you take this one.
Yeah. All right. This is interesting because there's actually, at the time we turned these slides in, there was some embargoed information, and so there's some late breaking news on this, but you might have heard late last year about an interstellar asteroid being discovered, which was a pretty significant thing because as was mentioned earlier, asteroids and comets are kind of the leftovers of solar system formation, and they get ejected from solar systems and they wander out in space. And so it's actually predicted that these things probably pass through our solar system. except it's never actually been seen. And one of the surveys funded by NASA that I mentioned earlier, the Pan-STARRS survey, as part of its normal survey operations looking for near-Earth asteroids and comets in the sky, it discovered something that had very interesting motion and not quite what was expected. And as they looked at the orbit, and as folks at the Center for Near-Earth Object Studies at JPL studied the trajectory, they tracked it back and then realized that, wow, this thing whipped around the sun and it came from above the plane of the solar system and it's heading out the other direction very fast. With this kind of speed, it couldn't have been something that was from our solar system. It couldn't have even been something that maybe it was like flung around by Jupiter and sent out of the solar system. This was something that came from outside the solar system. And the late breaking news this week was that it turns out it wasn't possibly an asteroid, but really perhaps a comet, because it's the motion as it was watched leaving, still continuing on its way out of the solar system, isn't what exactly you would expect from just the forces of gravity, from whipping around the sun and all. And it's indicating that there's probably jet activity like what you would see on comets with some gases coming off the surface, which would push it along a little bit. And so that's kind of the late breaking news, and you might see some news on that.
This forever, but we got to wrap it up and tell them what we're going to do if we find one on an impact trajectory to the Earth. Well, this is also fairly recent news, something that's been worked on for the last 3 or 4 years. In the administration, the White House released just a week and a half ago our new National Near-Earth Object Preparedness Strategy and Action Plan. This was work done by the U.S. government interagencies, departments and agencies across the U.S. government were involved in development of this action plan. And this lays out activities that these various departments need to take within the next 10 years to improve our preparedness for responding to a possible impact threat. The goals in the action plan are some of the things we've just been talking about. First of all, we've got to detect and characterize them and determine whether they're headed toward Earth or not. We need to be able to improve our prediction of first of all, whether it's going to impact or not, but also the characteristics of these objects, and knowing what we could do about it, the modeling of how we could deflect an asteroid from an impact trajectory. Then we got to develop those technologies and techniques to do the deflection. Also very important to the overall plan is increase the international cooperation. And then we're establishing the emergency response procedures and protocols as how's the government going to communicate amongst itself, communicate with the public about what's happening, and also internationally. Our leading technique that might be used, and you're going to hear a little bit more about it, is called the kinetic impactor. But all of these techniques work by just adjusting the speed of the asteroid by a small amount. It's just like two cars on the beltway that want to be in the same lane at the same time. Well, instead of colliding, the cars, one of them will adjust its speed by just a little bit so it can either go in front of the other car, or fall in behind. So for the Earth collision, to prevent an Earth collision, we either got to adjust the speed of Earth or the speed of the asteroid. I choose the asteroid. And so we just need to slow it down or speed it up just a little bit, so at that point in space where there would have been a collision, it will be a miss instead of a hit. We are working on a demonstration of this technology and technique with a project that has just been started and is about to be confirmed for its full development and launch later on. Launch in 2021 to encounter an asteroid system called Didymos in 2022, October 22, the double asteroid redirect test. And Cheryl is going to tell you a little bit more about this because she is the program manager for this project. So you've seen where this crater, talked about this crater before. We just asked that don't let this happen in your backyard, protect your local planetary defense officers. And now we'll take questions.
Okay.
So we have time for one question, so we're going to do a Facebook Live question from Doris. How many government organizations such as NASA exist worldwide?
Well, all of the world space agencies are participating in the United Nations Committee on Peaceful Uses of Outer Space. Member states, any country that has a member state that has space capabilities involved there. Tom mentioned the Space Mission Planning and Advisory Group. That is a forum for the world space agencies to get together, talk about collaborative projects and plans for mitigation techniques. And we have 13 different space agencies from around the world that are official members of that, and others that also attend as observers.
Thanks, Lindley and Kelly. I'll invite you back in just a few minutes.
Okay.
All right, well, we're going to move to the Wrap It Up presentation, and we're going to talk about NASA's first planetary defense mitigation mission, DART, the Double Asteroid Redirection Test. So I have a short video up here where you can actually see the DART spacecraft incoming to hit the small satellite in the Didymos system. So the Didymos system is a binary system. It's a two-body system, and that system allows us to be able to do this experiment. So we have two objects that are moving through space together. Both objects are rotating, and we have the satellite rotating around the primary object. So the big guy is about 800 meters in size, and the small satellite of the Didymos system, Didymos for twins, is about 160 meters. So what the DART project is going to do, we'll be ready to launch in 2021, is we're going to head out to the Didymos system, and Mother Nature is giving us a wonderful opportunity that this system will be very near Earth, just under 7 million miles. And it takes us about 16 months to get there, which is a very short mission from the perspective of planetary missions. And when we get there, as we go, we're going to put ourselves on a collision course in front of the small satellite, and we're going to steer our way in, and we're going to collide with the Didymos satellite. That we expect to make a crater, and we expect to see a big field of ejecta that will come out from that impact, and that will enable us to study what this type of a kinetic impactor does so that we can improve our models on space to help NASA do the predictions that they need to do in the event that there is a threat of this size of an asteroid coming towards the Earth. And in that case, then NASA could decide to launch 1, 2, or more kinetic impactors to go on out into the solar system and deflect this object. So what we're doing in this case for this experiment is we want to change the orbital period of the small satellite around the larger satellite. Right now, the orbital period is just under 12 hours, and we expect that we'll be able to, from the kinetic impact, change that orbit by about 7 minutes. Now, we're going to be able to observe this phenomena with all of the ground-based assets that Lindley and Kelly were talking about, and from all around the world. And this system will be close enough to the Earth that a 1 to 2 meter class telescope, an optical telescope, should also be able to observe this event. So we'll be enlisting astronomers from around the world to take advantage of observing this event. This period change, this propagation of the change will happen over about a 3-month period. We'll also be able to see it with radar. And we also have international collaboration on this project. We have several proposals on the table for collaboration. One is that we would actually carry a 6U CubeSat that would be piggyback, that we would deploy many hours before our actual impact, that could watch and document the impact. And we have collaborations with the European Space Agency as well. They're studying whether or not they could later send a post-impact observatory to rendezvous with the system and better study the damage that we have done. So it's a super cool mission, and it's a privilege on my part to be able to have this super cool job. to be able to manage NASA's first mitigation mission. So with that, it's time to invite all of our panel members back up here on stage, and we're going to open up to a question and answer center, not only for the questions here in the audience, the folks in the audience, but also online. And you can direct your question to any one of our panel members as well. And so we'll get started. Sir.
Yes, I have two questions. One is in the world map of documented impacts, the craters. The craters seem to be focused at mid-latitudes and not so much near the equator, not so much towards the poles. I don't know if this is a function of weather and erosion or what.
I would say it's actually an observation effect. In other words, the impactors really are randomly distributed around the planet, but the poles lack quite as much recordable terrain. And an ocean impact is really tough to monitor, except now we would see a tsunami wave or something like that.
A visual effect that it's on a Mercator projection. So, you know, the Mercator projection, the space at the poles is way spread out, much larger than it actually is in real life. So it's a visual effect because it's a Mercator projection.
Second question is there much conversation about the possibility of a body composed of dark matter that is undetectable to our current methods?
Wow.
Over my head.
Yeah, I don't think I want to try to take that either. I mean, dark matter, dark energy, we don't know how that physically manifests itself yet, so we really can't answer that question.
We're still learning.
With the DART mission, what kind of effects do you accept to observe that you can't model using kinematics?
Well, of course, we're going to, our models, we do have many models that exist. But we've not been able to actually have good flight data to be able to calibrate and validate those models. They're all analytical. So we want to do this demonstration so that we can actually feed that flight data back into the models themselves. We want to understand the ejecta. We want the way that the ejecta will go out, the way it'll reformulate, the footprint that it may make. It'll look like fresh material all around the mouth of the crater. What's the size of the crater? And we want to understand all of those dynamics and how they might affect and vary the models.
Yeah, because the point there with the ejecta is that, yes, you whack the asteroid, and that's going to give it a little push, but as the ejecta come off, that's also going to give a push. It's like a little extra rocket for it in a way. And so like you said, we can model that using kinematics, but until we actually try it, because it will depend on the composition of the asteroid, how dense it is, kind of don't know for sure until we try it. So that little extra push is something that's going to be very important to find out and test for this mission.
We expect that momentum to enhance.
Mm-hmm.
Are the velocity and the speeds, the velocity, the speeds of these asteroids, are they perpetual, or do they actually die down or decay, minus impacts, that is?
Well, they would only die down and decay if there's a force acting on it. And so if something passes close to another object, then that will affect its trajectory and speed. But there's not enough in space to slow it down. It's not like moving through an atmosphere where you have this pressure back on it. There's the density out in space is so low. It would really take something like interacting with another body. Or actually, there's the effect of sunlight. Sunlight on an asteroid can affect its spin and its speed slowly over time. Just that heating of one side of an asteroid and how that affects its motion.
It takes millions, tens of millions of years for that effect, though.
Right.
So there are many types of asteroids, and composition matters. And NASA has numerous programs that are studying asteroids, some of which as well as other nations, to bring samples back. Could you mention a little bit about some of the other missions?
Okay, well, this is very, very timely because there are 2 missions in flight right now going to 2 different asteroids to bring back samples so we can examine and know more about what asteroids are composed of. The first one is a Japanese mission called Hayabusa 2. It is going to the asteroid found by one of our surveys, Ryugu. It just arrived there at that asteroid last week. You can go online and see the fantastic images that are being returned by the Hayabusa 2 spacecraft of that little over half a mile sized asteroid. It has a very unique shape that we believe also the destination for our mission called the OSIRIS-REx mission. OSIRIS-REx is an acronym I'm not even going to try to break down for you. But OSIRIS-REx is the U.S. mission, also with international collaboration on the mission, going to asteroid Bennu, also found by one of our surveys, the linear survey. It will arrive at Bennu in August, starts its approach in August. Will go into what I would call station keeping with the asteroid. It's not really an orbit as you think about it. To study the asteroid for a couple of years and then collect a sample and bring back to Earth, which will arrive back here in 2023.
Great, thanks. Okay, next question from the audience.
Hi. Wasn't there talk recently about lassoing an astronaut or, an asteroid, or casting a big net over one and dragging it closer to the moon so we could study it better? Or am I imagining that?
No. There was a program within the last administration that was looking at how could we do human spaceflight to an asteroid. And in looking at what could be done in the nearer term, the systems for supporting astronauts out to an asteroid would have to be able to support them for at least a year, if not more, because that's the time it takes for interplanetary spaceflight, especially out and back. I think any astronaut wants to come back, so it's going to be a much longer mission.
Sign me up.
And so we were looking at what could be done in the near term to get astronauts to an asteroidal body, and the idea was that we could go out and take a boulder, one of these large boulders that you see on the surface of the asteroid, collect it up, and with solar electric propulsion, bring it back to the Earth-Moon system, put it in orbit around the Moon, and then the astronauts could go there, as well as it being studied by the Space Resources folks, looking at the composition and how much the abundance of water was in that sample.
All right.
Yeah, well, it was an exciting idea for an asteroid scientist and an astronaut to see astronauts interacting with an asteroid, and I think it was a very innovative and inventive idea to pluck a boulder off an asteroid and use a solar ion propulsion to bring it back into a nice orbit around the Moon where astronauts could reach it in the next 10 years. That was the idea. So we're going to see astronauts visit asteroids in the future. The experience that we're going to get returning to the Moon in the next 10 years is still not going to be enough to give us the deep space skills to go all the way to Mars in the early 2030s. I think there are going to have to be some intermediate steps, missions that last longer than a few weeks going to the Moon, stretching out to the 2.5-year round trip going to Mars. And a great way to get that intermediate experience is to go to the nearby asteroids and to have human explorers touch down or pull up alongside and dock with an asteroid gives us the deep space skills we need to encounter, for example, the small asteroid-like moons of Mars, Phobos and Deimos. And so we'll get the nearby rehearsals around the near-Earth asteroids that will enable us to go all the way to Mars. And as I mentioned in my talk, I think it's very important that we start harvesting the resources from the asteroids and the Moon to enable us to lower the cost of a future Mars expedition and to increase the radiation protection. We can just actually cloak a spacecraft with asteroid dirt and rocks. Here's, a chunk of an asteroid right here. Great radiation absorber if you can pile up enough of it in sandbags around your spacecraft. So there's a lot to be gained by first our robots paving the way and then astronauts following up with some very key expeditions to the nearby asteroids.
Okay. So what we're going to do, we'll take one more question from the audience, and then Rachel will do a Facebook question. We'll have to toggle back between our online guests and our guests that are here in the gallery. Sir.
It was very exciting times for NASA and for the planet to see all these adventures that you guys embark on. A question about the possibility of using lasers. There are this new breakthrough Starshot project, and also NASA, as far as I'm aware, has a Proxima Starshot project that uses a laser for interstellar space propulsion. And I understand that's going to be extremely powerful laser built for that. Can you please entertain an idea of using this type of extra powerful laser for deflection of asteroids?
Let me take that question. Yeah, we are aware of that project. Have talked with the folks. It still has a considerable amount of technology development to do. Having that a powerful laser, they want to station it in space. Would need to be maintained its operations for a long period of time in space. So they have some significant technology hurdles. If that technology comes along and they develop such a capability, we would certainly be interested in the other uses for it. But it's not technology that we currently have in hand, and so we're interested in something that can be used now in case we need it.
All right, Rachel, online question.
We're going to do a Facebook Live question from Roy. How large would an asteroid have to be an ELE? And if so, is there a contingency plan in place if that is a threat?
An LE, oh, okay. Well, that's not a term that we use in the real world. That comes out of the movie Deep Impact. But an extension level event. And I think, as you saw in some of the earlier presentations, the impact that caused the demise of the dinosaurs was an object about 6 miles across, 10 kilometers across. And although it led to extinction of several species on the Earth, life was not extinguished by it. So you're looking at objects that are 6, 10 miles or larger in size. We have found all the objects of that size in near Earth space. Anything of that size would have already appeared in our telescopes. So that's not something we have to worry about in the near term. Now, a couple of centuries from now, well, that's somebody else's watch.
All right. Next question.
Thanks for this great lecture. Does the Office of Planetary Defense have staff considering the societal or individual reaction to the knowledge of an asteroid being potentially on a course of impact?
Well, no, we don't on the NASA staff. But it is an issue that we are aware of and conscious of, and things that we need to take into consideration in our communications to the public should something be found. And that's why it is an interagency effort. It's not just NASA that's going to do it. The U.S. government, does have agencies that worry about those kinds of things. They would be involved with that aspect of it in helping us craft the right communications and how to tell the public about what's going to happen. Our job, though, is to have the capabilities to provide the best information available about whether such a thing is going to occur, where it might occur, and what the effects might be. So we're more on that science side of it, and we have other parts of the U.S. government that worry the societal parts of it.
May I add something to that? That is that you all remember the big solar eclipse last August and how many people traveled to go to the path of totality. I think as NASA gets more and more effective in identifying and tracking more and more asteroids, we're going to identify ones that are going to smack into the Earth but won't do any damage. They'll just be fireballs in the sky like we saw. You're going to have asteroid tourism taking place. And if the prediction is out 6 months in advance, there are going to be tour operators and cruise ships going to the impact location to watch the spectacular fireball. And sign me up.
There you go. All right, we have an online question? No? All right.
Oh.
Young lady, your question.
Mr. Jones, what does outer space look like?
What does outer space look like? Well, we're here in the Moving Beyond Earth gallery at the National Air and Space Museum. You've got a great view on the video screen up there of what the Earth looks like from the space station. That's a pretty close approximation. If you go to one of the great IMAX movies that's playing here in the museum, Journey to Space, A Beautiful Planet is my favorite space visual movie. It's called A Beautiful Planet, and that one gives you the real astronaut's eye view of the Earth from the space station. So that's one I encourage you to go and see. And what I can just tell you is that for an astronaut like me who's only been up in space 240 miles or so away, the Earth really fills half of your sky. Sometimes it's beneath you, and as your spaceship rotates or does its job and turns around, sometimes the Earth might be filling the entire sky. So one of the marvelous things is that no matter which window you look out of on the space station, for example, you're going to see some beautiful view of Earth. And it's such a gorgeous view of our planet. It is so lovely it brings tears to your eyes sometimes. And that makes you realize inside how important it is to protect it from one of these future asteroid impacts.
All right.
Tom wouldn't say it, but he wrote a book called Ask the Astronaut, and he's going to be around for a book signing later.
Yeah, I forgot. Thank you, Jim. 2 to 4 o'clock, I'll be outside the store signing my books, Ask the Astronaut and Skywalking. So I look forward to seeing you there.
All right, we've talked a lot about Earth impacts in terms of the ground, but we get a lot of asteroids that also, or meteors that will go into the sea, and we could potentially have the effect of tsunami. Anybody like to say a few words about that?
Well, I think the Japan situation really attuned the world to how bad tsunamis can be. And the impacts, like that modeling of the Chesapeake Bay impact, the tsunami wave is enormous compared to what Japan had to deal with. I want to say it was like a 100-meter high wave, not a 5 or 10 meter. I mean, these can be very large sea waves as they come up the continental shelf. So tsunamis are a real concern that hasn't gotten the attention I think that it might deserve.
All right, we have one more audience question.
So instead of deep impact, let's talk about Lucifer's hammer. Comets, because of the difference in composition, is it a different type of threat for us?
It is important because comets can be faster. We have talked about the size of the impact involves the size of the impacting object, but comets can be twice as fast depending on how they're arriving. So that can be a serious threat that it's hard to predict when a comet would come from this cloud that's out there. Little subtle perturbations will cause it to come into the inner solar system. I am not aware of a way to predict comet impact problems.
Well, let me say a couple of things about it. One, we have somewhat of an advantage of comets because they reveal their position a lot easier than asteroids do because of the gas and volatiles that get heated by the sun, and that expends the dust clouds from them, and they create this tail. And so you can see a comet out at the orbit of Jupiter or so. So they announce their arrival a lot easier than the asteroids do. The asteroids, a lot of them are very dark, and it's like, you know, trying to spot a candle at the distance of the moon to be able to detect these asteroids. But even if you find them at the orbit of Jupiter, if they were on a direct trajectory to impact the Earth, that only gives you a few months of warning. Admittedly, we have that problem. However, in most cases, the comet's going to come through the inner solar system 2 or 3 times before it would impact the Earth, and so we just need to be looking for them. Space is a very big place. I don't think, other than Tom up here, has a real sense of how big space really is. And as you saw on my charts, the inner solar system comet population, those that come within the inner solar system, is much smaller than the number of asteroids are out there. There were only 107 comets compared to 18,000 asteroids that we've discovered. So the risk from a comet impact is probably less than 1% of the risk from an asteroid impact. So let's figure out how to take care of the asteroids first, and we'll work the comets.
Yeah, in 100 years, we're going to have gravity tractor beams, and we're going to have interstellar flight, and all of that will take care of the comets for us.
All right. Well, thank you. We're going to have to wrap up our event here today. I'd very much like to thank the National Air and Space Museum, the Boeing Company, and Asteroid Day for sponsoring this event here. I hope that you have enjoyed it. Thanks to all of our guests for coming out and to NASA as well. And thank all of you for participating so well.
Thank you.